Hello, we are Team25 and we will be presenting our movie recommendation system. We will first describe our overall system architecture and discuss the key design decisions we have made and discuss reflections for the overall project. So this is how our overall system architecture looks like. The first component is data collection, where we collect user and movie data using Kafka and API provider. Users send their watch logs through Kafka, and using those information, we fetch user and movie data through a given API provider. And using the recently collected data from the previous step, we train the model. We have trained two models with different training techniques. The primary model uses a collaborative filtering, and the secondary model uses a content-based filtering. These models are updated with the most recent logs every 3 hours, and their version metadata are kept tracked for provenance. Once the user requests for a movie recommendation through the API service, the recommendation service returns a list of 16 movies, which are generated from the model inference. Using those recommended movies, in addition to the past record of recommendations, we conduct an online evaluation and experiments on both models by using top K hit rate metrics. And all requests for the recommendation, watch logs, and recommendation results are monitored through Grafana Cloud.
Yeah, so the second part, we're gonna go through two key design decisions. The first one is we adopt a MySQL database to do all the data storage, to store the movie user data and all the logs instead of listening everything from the Kafka listener. So this choice has three main advantages. The first one is very efficient because we only have to pre-process every data entry only once. And the second is better for us to reproduce everything because the data is stored locally and always available for reproducing the models and recommendations. And the third advantage is it's very robust. All those training, evaluation, and API services are always robust against incidents on Kafka listeners. So we also have some drawbacks for adopting those databases. It requires more memory and bandwidth and could introduce system bottlenecks, but we believe the benefits is more than the drawbacks. Yeah. So the second design decision, we containerize all the services in Docker. So this includes the API service, the recommended service, the online evaluation, the experiments, the listeners, and the training service, and also the monitoring dashboard. So the first advantage is we modelize everything, so all services are independent from each other. So even though one crash will not affect the others. And the second advantage is very flexible. We can easily retrain models, deploy models, and change the number of distributed services for flexibility. And the third thing is it's very robust. We always have a backup service, so the overall system is robust to extreme cases. Yeah.
So for the next part, we'll talk about two reflections. And the first reflection is about our monitoring dashboard. So as you can see in the left chart, this is our current monitoring dashboard. It only includes the amount of our valid and invalid watching log, rating log, and the recommendation logs. So one reflection we are currently make is we cannot check the types of error with our current dashboard, and we can only get the information about the valid data. So our solution is, so first we could add a Kafka data check. So specifically, first the data drift, we can check the user average age and occupation categories or any other user and movie data, and we can put them in the dashboard. And then secondly, we can add the data quality check. For instance, we can list the reason of each invalid dashboard. For instance, the invalid timestamp type format. So another thing we could add it on our monitoring dashboard is we could add the number of effective watch, which could check our recommendation system. And secondly, we could also add the number of new user and then the number of new movie currently loop into the system.
Apart from our reflection on these recommendation services, we also have some reflections on our teamwork. First, on team synchronization. One challenge we faced was synchronizing our work during collaborative development. At times, multiple team members were rebuilding Docker images or modifying shared components at the same time, which led to confusion and duplicated work. While we did set up a lightweight task board, we didn't update it frequently enough for it to be fully effective. To improve coordination, we made a conscious effort to increase transparency by sharing our actions more regularly in the group chat. This simple habit helped reduce conflicts and improved alignment during parallel work. Second, on skill-based workload assignment. Initially, we assigned the tasks based on mostly on preference or who was available, rather than matching responsibility to technical strengths. Over time, we realized that a more thoughtful skill-based approach could have improved efficiency. For example, one teammate has prior experience with Grafana and was able to lead our monitoring setup. If we have accessed each person's expertise earlier, we could have allocated tasks more strategically and reduce onboarding time for certain components. Third, on data versus deployment groups. Looking back, another structural improvement would have been to divide our team into specialized groups, a data group and a deployment group. The data group will focus on data collection, quality checks, and modeling, while the deployment group could concentrate on infrastructure, CI/CD pipelines, monitoring, and provenance. This division could help prevent overlaps, deepen focus within each area, and streamline handoff between different parts of the pipeline. And the above is all the contents we plan to share, and thank you for listening.